Hello everyone. In a previous video you might have seen that Psychotic Break is getting a version 2 overhaul, and I am moving the weapon drive system over from a belt to a direct drive hub motor. So what I wanted to do in this video is give you a little bit better idea of everything that I've learned in iterating various different hub motor designs, because there's a couple little gotchas and a couple little things I've learned along the way. So let's take a look at hub motors, what they are, what the benefits are, what the cons are, and how you can design your very own hub motor. So before we get started, I do want to say that I am not an expert in hub motors. There's a lot of people that have done a lot more hub motors than me. I've only kind of done a couple over the years. However, I am the one doing this video. A lot of people don't really do videos, so I've kind of gathered up all the information, and I've definitely prototyped a little bit and learned some myself. So I'm going to try and just kind of give you at least an introduction, and maybe eventually I'll do kind of a more advanced video. But for right now, this is just all the stuff that I've learned over the weeks of dealing with hub motors. So what is a hub motor? Well, in the traditional design, you have, a motor like this little outrunner right here. I'll show this up close later, and it has a pulley on it. You have a belt, and that drives something else. You have, kind of two mechanical pieces that are moving. In a hub motor, you basically have a motor that is directly driving the thing. So like for my very first combat robot, Sergeant Cuddles, the motor can is inside this drum, and the outside of the can is directly coupled with the weapon, and that's what's doing the spinning. You might hear hub motors referred to as direct drive. So you could take a wheel or anything else and put it directly on the outside of this can, and that is directly the thing driving. So basically a hub motor is you're directly driving the thing that you're doing. So in this case, I have the weapon motor completely built into the weapon. This would be a hub motor or a direct drive system. So that's the what, here's the why. A hub motor has a couple benefits. They have a couple pros, a couple cons over a traditional motor. At least for me, I have not had great luck with belts and pulleys and things like that. So you get rid of the whole concept of belts and pulleys. If you have one motor here and the other thing over here, you basically have to have two moving pieces. This has to spin and be nice and constrained, and then over here this thing needs to be strained, and then you have the belt as the weak link between those. So you get rid of the concept of belts and pulleys and all that other stuff. You are directly driving the thing. So in a combat robot scenario, you are removing one more potential weak link, which is that belt or chain or whatever it is that links the two together. So that is a benefit. The other benefit is you get to directly drive the weapon. So sometimes in a space constraint situation, Sergeant Cuddles is a great example. If I wanted to put the motor somewhere in here and then drive a belt to it, there's really no room inside here. That's where the drive motors go. So it removes that concept of having to have something remotely located. You can just have the motor right where it needs to be, right at the wheels, right at the weapon, things like that. Other benefits, it can typically be more robust because you don't have these two mechanical systems. You can kind of combine them into one, and you have a much more robust and reliable weapon system or drive motor. Now, cons are kind of interesting because depending on how you implement them, they can be a factor or not. Well, in this case, you have everything in here. So when I take a hit or I dish out a hit, guess what's going to happen? This mechanism or this assembly is going to be taking all that force and all that load, which is going right into your weapon. If you use a belt system, you're kind of removing that from the motor itself. You're transferring it away, and the belt or that connecting mechanism is really the thing that's taking that shock and force. You're moving it outside of the motor so it can help protect your motors better. However, I think a well-implemented hub motor setup, you can kind of get rid of that problem. So yeah, more shock into the specific motor itself. The other issue in an ant weight or beetle weight class is the kV rating of the actual motor. You might not always find a motor that will work in this situation because the kV rating, or the ultimate RPM rating, kV times volts equals RPMs, the kV rating might not be proper for this. I'm using these really weird motors that I won't post a link. I can't find these anymore. I bought all that I could find, so they don't really exist anymore. And these have a relatively low kV rating, which means that my final RPM is about where I want it to be. most will have a much higher KV rating, especially when you think of doing this for driver wheels. You need maybe a KV rating at like, 50 to 80 or maybe even 100, which is just not common in these small cases. So that's kind of some of the pros and cons. I guess another con is they are more complicated. Taking this, putting a pulley on it, driving a belt to something else is very easy. Designing, parts like this and manufacturing and making parts like this is a little bit more complicated. However, in something like Sergeant Cuddles, this is relatively easy to do. So in summary, it can be more robust, can be a little bit more efficient, a little bit more battle hardened, less prone to failure, but it is a little bit more complex to design and just kind of harder in general to do so. So let's take a look at some brushless outrunner motors for those of you just kind of not familiar with the basics. So this motor kind of gives you a really good idea what's going on here. We got the stator and the windings on the inside, and then you can see the outside of the can moves. Now if we look really closely, you can see that the stator is very, very close to the magnets on the outside. There's only fraction of a millimeter gap in between these two, so that will come into play later. But we can see the whole outside of this can moves and the base stays stationary. So very simply, if we just kind of bolt something onto the outside of the can, that will move it. So this is how Sergeant Cuddles' weapon works, is just you press the drum over the outside, that spins, and that is all there is to it. Now if we take off the little clip on the bottom, you can separate the two halves, and it gives us a little bit better look at what's going on inside one of these motors. This is, I think, one of the dead motors from Psychotic Break version 1, and you can see there are the windings, that is the stator, and then you can see just the actual motor structure there. Now the one thing that you'll notice is on the inside there's a very little tiny bearing. Look at that little cute guy. We want to use something a lot bigger than that. And you notice there's one bearing there, one bearing there. This helps to line up the shaft perpendicular to the can, so when this goes in there, it can't shift around like that, and it can't shift around like that. It is going to be perfectly centered in the middle of that motor, and then it can spin nice and freely. If it's off to one side, it's going to knock against the side, or if it's kind of like that, somewhere like that, it's going to also rub against it. So we need to make sure that when we design a hub motor, that all of this is perfectly concentric in with the stator, and that nothing can move around like that either. So when designing a hub motor, there's a few things that you need to keep in mind. Basically what we're doing is we're taking off this ring of magnets, so you can kind of like cut it right there and you're just left with this ring. We're going to put this ring inside of something, then we're going to take that, do something like that. So now this hat, if you will, is this piece. So that's what's spinning around, and that gives us a different point to mount our weapon to. So now the weapon is actually mounted to this nice big beefy piece. This holds the magnet ring, and then it allows us to use some much larger bearings. This was my first iteration of this attempt, and you can take these motors and you can kind of press out these bearings. You just kind of put something inside and then tap it out from the back side. Once you get one out, then you can tap the other out, and then it allows you to use a much larger shaft, something like that. So what I originally did is tap the bearings out of this, and then put the can inside of there, and then I have this little thing that goes on top, and that's what holds it. Here's the problem. If you're just using a single bearing, when this goes through, no matter how tight it is, this can still wiggle a little bit. The race of the inside of the bearing is not perfectly perpendicular to the outer race at all times. There's a little bit of wiggle room. So even though this is tight in this direction and this direction, it doesn't really move up and down or left and right. That is constrained, and that is because the bore of this matches the bore of this. Those fit nice and cleanly together, but the inner race and the outer race have a little bit of play to them, so this will move. Now what happens here is that means that the magnet ring is going to do this, and it's going to kind of touch and rub against one side, and you might end up getting it kind of moving like that. So you really need two bearings, or at least you need to constrain the shaft in not only the X and the Y direction, but also kind of in the pitch. It needs to not be able to kind of rotate around like that. So this brings me to version 2. Version 2, I went a little bit different and used two smaller bearings, mostly because of the height. I need this to fit into a very specific height. So I have one bearing that sits on the outside, another bearing that sits on the inside. I don't know if I can press this one in there. So one there and one there, separated by a lip. And then this sits on top. So now the shaft is going to be going through 1 and 2 bearings that are both concentric, so they're lined up over top of each other. And when the shaft goes through, it can't wiggle around because it's going straight through both of these bearings. This helped quite a bit. The main issue I had with this is I was really sloppy when I machined it. Let's see if I can press this in. It was really sloppy when I put this thing together, and there is too much play in everything. So this top bearing actually has a little bit of shift to it, and that created an issue. So everything has to be pretty darn snug for this to work right. So in this case, I'm trying to move it here. There's almost no wiggle room. This shaft is pretty much perfectly stationary, which is nice. So this is a nice, good next step. Now let me show you what actually works. Here is the final version of the hub motor. It's very similar to the last one. It's just that everything's a little bit more precise and a little bit tighter tolerance, so it actually works. The one thing to note is that unless this is bolted into something, it's really rough. Like, I can't really demonstrate this, but it's really rough in this because this all needs to be bolted into something and then it actually gets smooth. So something to keep in mind. It will be really rough until you get it fully constrained. So we've got a 10 millimeter shoulder bolt running through the middle of this. And I've just got a couple bearing spacers here just because this little cap rises above the race right here in the middle. So I'm just using some spacers to just kind of get it up and above that so I can smash it in. This is going to be held the same way as my other Psychotic Break, to where you're going to have something here and something there, so it's going to spin in the middle of that. So just take that into consideration. We've got our motor in the bottom, so I'm going to go ahead and pull this out. We've got another spacer in there. This spaces us off of this bearing that is pressed inside. So we've got one bearing here, and then one bearing that is held in place by this top cap. And so those two bearings are concentric, and so that when I put this bolt through, the races of these can't do that because they are concentric with each other. And it fits in pretty tight, and yeah, you can see it spins nice and freely with those two bearings. And I can't get any wiggle out of it. This shaft really just doesn't wiggle whatsoever, which is nice. And then you can also see, let's get that out of there. You can also see the motor ring inside there, the magnet ring. This one hasn't been epoxied yet or anything. This one's pressed in there pretty tight, nothing crazy, but it is pressed in there relatively snug. You can see in the corners I have 4 little holes. These are drilled and tapped, and if I screw 632 screws into there, it actually presses against the ring and brings it out. So that's what these 4 additional screws are for. It's for pressing out this motor ring, because once it's in there, there is no real way to get it out. The other feature, so we're using a spacer against that bearing. That lifts this up just enough so that when the motor goes in there, the top of these windings don't rub against the base, and that this surface is pressed nicely against the inner race of that bearing, so those glide against each other. And then I also had to bore out the center of this motor, remove the bearings, and bored it out, or reamed it, actually using a reamer, so that it fits the 10 millimeter shaft right there. Now, this isn't actually all that critical because the motor itself is going to be bolted into something. So this and this will be, I guess, on the same perpendicular plane like that, because the hole that this goes through is also going to be bolted to the bottom of the motor. So those two things are going to be always pretty well lined up. So yeah, that gives you a little bit better idea of how this assembly fits together. Let me just take off the top cap of this just to show you. So this little top cap here really isn't all that critical. I actually don't think I completely need it because the bearing will be held in place by the bolt that goes through the whole assembly, and this whole thing gets kind of squished with the top and the bottom frame. So it's really not that necessary, but I wanted to prevent anything from happening to it. So I just have this little machined piece here that just kind of holds it in place, and it just kind of fits nice and snug over top and then is held in place by these screws. So yeah, that's pretty much all there is to it. So let me put this back together and then I'll show you, it working on this little metal plate that I made just as an example, but kind of gives you an idea of how the hub motor all goes together. So a quick note about this, as you see I have the 4 holes that correspond to the bottom of the motor, and then I have a tapped hole that is for the actual shaft or the shoulder bolt that goes through this. For the actual implementation, this is going to be a through hole, not a tapped hole, and I'll just have a nut or something like that on the bottom. But one interesting thing is for these 4 motor holes, or for this, you don't necessarily want all of these to be very tight fitting. You want the motor to be able to kind of shift around a little bit, and then you tighten it down. Right now everything's kind of loose, and it has a little bit of play, it has a little bit of wiggle, and it does have some like kind of spots that we'll want to catch on. You want to kind of tighten one, then tighten the other. And if you're going to use countersunk bolts for this, you want your center shaft to have maybe a little bit of play. It's going to be very difficult to get all of these perfectly lined up. So if you use countersink and a tapped hole, they might be off just slightly and they might be fighting against each other. So just keep that in mind. So now once I tighten these down and then tighten this, there, now it's nice and smooth, and there's no grinding, no rubbing. It's all perfectly concentric. So I guess the last thing to do in this video is to show this working. I've got this clamped down to my workbench, and I'll be, somewhere else in the shop while this is running. This is just an MDF weapon. It's nothing too powerful. I calculate that this is like 50 joules. The motor that's in here is about half of the kV that I will be using, so this spins a lot slower than the final one, just an FYI. This is using the same electronics as my other stuff. It is a Multistar 51A BL Heli 32. I'll go into that in future videos, but same exact electronic setup as the previous Psychotic Break, so nothing too fancy or special here. So let's plug in the battery and get this thing spinning. So there you go, Psychotic Break's new hub motor. So hopefully this gives you a little bit of an introduction into hub motors and the things that you need to know while designing them. I guess the short takeaway here is that you need to make sure that all the components in the stack up cannot move like this, they can't shift around each other, they can't shift like this, and they're all nice and concentric and lined up and constrained in all those different orientations. Having the 2 bearings is absolutely critical. Trust me, I tried getting away with just 1 big bearing. It's just not really going to work out that well. There are bearing types that the inner and outer races are fixed to each other. I think you could probably do a tape of roller bearing, things like that. But generally speaking, you're going to want to use 2 bearings lined up. You could even do a bearing on the bottom, bearing on the top, whatever, just as long as those things are lined up so the can can't shift around and touch the stator. So I think that's the biggest thing to keep in mind. Just a lot of spacing and tolerance issues are all the things that I ran into while making this. But generally pretty pleased with how it went. Now I got to move on and do the rest of the robot. But as always, thanks for watching. Check out the links below for other things, and check out my Facebook page for channel updates and whatnot. And if you want to help support the channel, there's an Amazon link down below that you can use to help support this channel and all the little things I'm doing. So as always, thanks for watching. See you next time.